Hello. In the next couple of videos, we're going to go over section 3.3 from the Lock 5 textbook, constructing bootstrap confidence intervals. So we talked about confidence intervals in the last section, and then we're going to focus on what this bootstrapping is in section 3.3. All right, so we'll talk about what a bootstrap sample is. We'll talk about bootstrap distribution. Then we'll learn how to compute standard error from a bootstrap distribution. And then we'll figure out how to compute a 95% confidence interval using the standard error from these bootstrap distributions. First, let's do a little review. Suppose you want to estimate population parameter. You each collect data, collect your sample statistic and standard error, and compute a 95% confidence interval. And let's suppose you computed 112 different confidence intervals. If you imagine there's 112 students in a class and every student has to collect their own data, find a slightly different mean and standard error. How many of these student confidence intervals, 112, will contain the true population parameter? Well, to get this, we know that about 95% in this confidence interval definition means that 95% of the intervals should contain the true population parameter, which would be about 106. If we multiply 112 by 0.95, the closest of these values is 106. So also review kind of what we talked about in section 3.2 is what exactly is this confidence interval that we're talking about? We want to know something about a population. We take a sample. In this one sample, we can compute a statistic, say a sample mean or a sample proportion. And then we want to add and subtract this margin of error. So how do we get this margin of error? We would take many samples. And out of these many samples, we could compute a statistic for each sample. Imagine if we're computing a mean, we can get a sample mean from one sample, but then we're going to take many samples, calculate a statistic for each of these samples, and then create a sampling distribution, as you can see down here, dot plot, that has all the different means plotted. The standard error is the standard deviation of the sampling distribution. So the standard error is the spread of the sampling distribution. And then if we want to find a 95% confidence interval, the margin of error is twice or 2 times the standard error. And that then gives us the ability to compute a confidence interval. All right, so as a summary, we create to create a plausible range of values for the population parameter, take many random samples from the population, compute sample statistics for each different sample, compute the standard error as the standard deviation of all these samples, and then we're going to use the statistic from one sample plus or minus 2 times the standard error to find your confidence interval. But there's one small problem. Actually, now I'd probably say it's a very big problem. Oftentimes, most of the time, we're only going to have one sample. Finding a good sample is difficult, time-consuming, and costly, time and money. We talked about in chapter 1, it's hard to get a sample that is truly random and representative of the population. So oftentimes we'll just have one sample. So how do we know how much sample statistics vary if we only have one sample? All right, well, that's our new topic for section 3.3 is the idea of taking a bootstrap. All right, hopefully you're not hungry because we're going to talk about Reese's Pieces. Let's say we have one Reese's Pieces sample. And there's 100 Reese's Pieces, and 52 out of those 100 are orange. So we get a p-hat of 0.52, a sample statistic. Well, where might the true p be, the actual true population parameter, the proportion of all Reese's Pieces that are orange? So unless we could count every single Reese's Pieces in the world, and I would say that's impossible because they're constantly getting made and consumed, so it's impossible to get the population. We can consider the population as many copies of just the one original sample. So what do we have to assume? We have to assume that this would be one sample, 100 Reese's Pieces, 52 are orange. And what we're going to do with this bootstrapping technique is turn that one sample into many, many, many repeated samples from this population. So we're going to take one sample and kind of repeat it. We're going to bootstrap it. Talk about that in a second. So to simulate a sampling distribution, again, simulate, it's very difficult to get a sampling distribution. It's hard, costly, time, and money to get many, many samples. So what we're going to do with this bootstrapping approach is just take repeated random samples from this population, made up of many copies of the sample. And in practice, of course, we can't actually make infinite copies of the sample, but we can do this by sampling with replacement from the sample that we have. So keep in mind, we're going to have one specific, one fixed sample, but we're going to repeat this sample with replacement. All right, so let's take this as a little visual example. Let's say we have a random sample of 6 people that we visualize right here. The 6 different people in the sample. There's our original sample. And we're going to do a simulated population to sample from. So we're going to use this one sample of 6 to create a bigger population. And we're going to do that with the bootstrap. The bootstrap sample is to sample with replacement from the original sample using the same sample size. All right, so how does this work? We're going to randomly pick one person from the sample. Okay, we've got the blue person, blonde hair. But then we're going to do with replacement. So we're going to take out this person to make a new sample, but then put them back in. Shuffle it up, and then grab another person from the sample, put them back in the sample, shuffle it up, and take another random sample. So notice we could end up with the same data point twice in a bootstrap. That is allowed. And that comes from the sampling with replacement. All right, then we take this bottom circular person, but then for the bootstrapping, we're going to then put them back. Reshuffle. Oh, look, we got that same person again. And then we've got the person with the glasses. So we created a bootstrap sample from the original sample. So notice we could have repeated values because we're with replacement, and the sample size is 6. We're going to make sure that we have the same exact sample size. Okay, so let's suppose we have an original sample that has these 5 data points, 18, 19, 19, 20, 21. Is the following a possible bootstrap sample? Answer for this one is no. And that is because 22 is in the bootstrap sample, but it's not in the original. Everything in the bootstrap must come from the original sample. All right, same original sample data. Is the following a possible bootstrap? 18, 19, 20, 21. And the answer to this is no. Bootstrap samples must be the same size. This is a sample size 4, but the original sample is sample size 5. All right, we've got the same original sample, and now we've got the following sample, 18, 18, 19, 20, 21. Is this a possible bootstrap sample? And the answer is yes, in this case. It's the same sample size, and every single number in here does belong in the original sample. Notice we got 18 twice, but that's okay because we sample with replacement when we do the bootstrap approach. So a bootstrap sample is a random sample taken with replacement from the original sample, and it has to have the same size as the original sample. A bootstrap statistic is the statistic computed from or on a bootstrap sample. And a bootstrap distribution is the distribution of many, many bootstrap statistics. So here's a kind of a way to visualize what we're doing with this bootstrap. We have the original sample, and this is just one sample. That's all we have in terms of hard data. And then we can compute a sample statistic. It could be an X bar, sample mean, or P hat, sample proportion. And then from this original sample, we're going to compute different bootstrap samples. So notice these arrows, all these bootstrap samples come from the one sample. These come from randomly picking data points from this original sample, but then replacing, reshuffling, picking again, all the same sample size. And from these bootstrap samples, we're going to compute a whole bunch of different bootstrap statistics. From these bootstrap statistics, we're going to create a bootstrap distribution. And from this bootstrap distribution, and from this, we're going to compute the standard error and the margin of error. So we're going to come back to that a little bit later on. Let's do a couple questions. If you have a sample size of 50, so you have one sample size 50, and you sample with replacement 1,000 times to create 1,000 bootstrap samples, what is the sample size of each bootstrap sample? Answer is 50. We want to make sure the bootstrap samples are all the same size as the original sample. If you have a sample of size 50 and you do a sample with replacement 1,000 times to get 1,000 bootstrap samples, how many bootstrap statistics will you have? 50 or 1,000? And here you have 1,000. One bootstrap statistic for each bootstrap sample. So you'd have your sample statistic from the 50, the original sample statistic, and then you would create 1,000 bootstrap samples in this example. All right, so here we have a bootstrap for one categorical variable. I'm going to go show you a stat key in the next video. But here we're looking at the original. This is going back to the Reese's Pieces. If you had 100 in your original sample, and 52 were the orange Reese's Pieces. And what we're seeing right here is a sampling distribution, a bootstrap sampling distribution of 1,000 samples. So each dot on here represents a bootstrap sample of size 100 that'll have different various bootstrap sample statistics. And notice right here we can compute the standard deviation of 0.05. This comes from the bootstrap distribution, and we're going to call this the standard error, because the standard error is the standard deviation of the sampling distribution. All right, one last thing we'll talk about before we break and finish the chapter in later videos. Why bootstrap? So bootstrap comes from the phrase pull yourself up by your bootstraps. The idea is you lift yourself in the air simply by pulling up on the laces of your boots. The metaphor is for accomplishing an impossible task without any outside help. So the reason why we call it bootstrap in statistics is we're going to use one sample to then create a whole bunch of different samples that we can then create a sampling distribution. So we'll talk about this some more in the next video.